Okay, welcome to the 8.4 notes on the area between curves. Today we're going to find the area enclosed between the graphs of two different functions. To this point, we have calculated the area of a region enclosed by a curve in the x-axis as shown in this blue graph right here. We know that this function, 1/2 x plus sine x, integrated from 2 to 16 would yield the area that's shaded in blue here with the diagonal lines. And of course, you can calculate that using your calculator, using algebra, and it approximately ends up being 63.542 units squared. Back in earlier math courses, you may have found the area of a complex region, such as this one here, where we have a gray circle and a white square. And the idea of the question is to find the area just of the gray region. And to find the area of that shaded region, you may have found the area of the circle and then subtract the area of the square. So in this case, the radius of the circle is 4 centimeters, and the side length of the square is 3 centimeters. So the area is pi r squared minus side squared. So pi times 4 squared is 16 pi minus 9, and that would be the area of the shaded region. And I forgot to type in that would be in square centimeters. Today, we're going to find the area enclosed between two separate curves. It is very similar to that concept of subtracting areas of composite figures. So let's take a look at two different parabolas, one of which is opening upwards. F of x is x minus 2 squared plus 1. G of x is negative x minus 2 squared plus 3. And let's say I wanted to find the area of the pink region right here. Well, of course, it goes from the intersection of the graphs, from one intersection to the other. And we would take the region enclosed by the blue curve in the x-axis, so this region marked Roman numeral 1 here, and then you'd subtract away the other area between the red function labeled Roman numeral 2. In summary, the pink area is equal to the blue area minus the red area, and hopefully you can see that visually. And in algebraic sort of notation here, or calculus notation, we say the integral between the difference of the two functions is the integral of the upper function that's above or greater than the other function minus the area of the function that is less than or lower than the other function. That leads us to the big idea of today, the area of a region between two curves. If two functions f and g are continuous on the closed interval from a to b, and we know that one function g of x is less than or equal to the other function f of x for all x in that closed interval a to b, then the area of the region bounded by the graph of f, the graph of g, and the vertical lines x equals a and x equals b is the integral from a to b of f of x minus g of x dx. Okay, and it doesn't necessarily have to go between the two intersection points, although that is very common. You might just give two other lines, x equals a and x equals b. For example, in 8.4.1, let's find the area of the region bounded by the graphs of y equals x squared plus 2, y equals negative x equals 0, and x equals 1. Sketch and shade the region. First, let's graph y equals x squared plus 2. That has a y-intercept of 2. That function is a parabola with an a value of 1. And if you remember from Algebra 2 and Algebra 1, when you graph parabolas, you use something called the parent function. And so the parent function had us use x values, and typically your teacher would either use negative 2 to positive 2, or they might just do 0, 1, and 2. Then they would square those values, x squared, and you'd get 4, 1, 0, 1, and 4. And then you'd multiply by the a value. In this case, the a value is 1 times x squared. This is usually a times x. And so, of course, the middle column just remains the same. In the last column, I just multiply this middle column by 1, the a value, 4 times 1, 1 times 1, 0 times 1, and so on. And then you cross out that middle column and just graph the ordered pairs formed by the first and the third column. And we graph those ordered pairs from the vertex. And the vertex would be at h comma k. And that's for a function in the form y equals a times x minus h squared plus k. Excuse me. In this case, we know that the h value in our function is 0 because it's x minus 0 squared times 1 plus the 2. And so my vertex in this problem is 0, 2, as I've labeled in the graph. And then I would graph those ordered pairs from that vertex. So I go negative 2 from that vertex, 1, 2, and then up 4, that's off the graph. Negative 1, up 1, 0, 0, 1, 1. And of course, 2, 4 is also off the graph. So I'm just going to sketch that parabola here. It's not going to be perfect, but you're going to get the idea that it is a parabola. There you go. Let's graph the other function, y equals negative x. Of course, this has a y-intercept of 0 and a slope of negative 1. So I'll go down 1 over 1, down 1 over 1, down 1 over 1. And then you'll draw a line connecting all those dots. Okay. Let's graph the line x equals 0. Well, x equals 0 states that for every y value, x is 0. So that's going to be a vertical line going up and down on the y-axis. Oops, missed that one. Let's try it again. And then let's graph the last vertical line, which is x equals 1. For every y value, the x value is 1. And so now we want to get the region bounded by those. So you can think of these as sort of the fence posts, and inside all of the fences is the area we want. And I'm just going to highlight that in green here. Actually, let's use orange because I haven't used orange in any other graph. So here's the region I want, right there. And it's clear, hopefully, to you that this would be very hard to get the actual area of if we tried to use geometric formulas or anything that you learned in Algebra 1 and geometry. And that's why calculus is a useful tool, because now I could find the exact area using a limit of Riemann sums or rectangles and just definite integration in the fundamental theorem of calculus. So let's go ahead and evaluate this. And when I set up the integral, what I want to do is figure out which region is greater than, or which function, excuse me, is greater than the other function in terms of the red and the blue. And so it should be clear to you, hopefully, that the red function, y equals x squared plus 2, is going to be greater than the other function, y equals negative x, over the entire interval. So for this, in this case, the red function is larger than the blue function because the y values are greater or above the other one. And so when I set up my definite integral, we know that, and I'll set up the bounds later, but for right now we know that the top function, x squared plus 2, would go first, and then I would subtract away the smaller function, or the function that's below negative x, dx. Now the bounds of the integral will be the left and right, how far you're going on the x-axis, and of course we're bounded by x equals 0 and x equals 1. So in this case, the lower bound would be 0, the upper bound would be 1, and you just integrate with respect to the variable x. And now let's use the just general integration rules that we know. We'll do this by hand without a calculator because that might be the case on the AP exam, that you have to integrate using just general formulas. So in this case, it would be x to the third over 3 plus 2x. And this is going to be a negative x, so it's a positive x. That becomes x squared over 2. And we're going to evaluate that integral from the x values 0 to 1 using the fundamental theorem of calculus. So I get 1/3 plus 2 times 1 plus 1 over 2 minus 0. And so in that case, we're going to take the fractions, get a common denominator. I'm going to get 6 as the denominator, so I have 2 over 6 plus, and this would be 12 over 6 plus 3 over 6. I'm just taking these 1/3 and 1/2 and the constant 2, making them over 6. And then 12 plus 5 would be 17 over 6, or 2 5/6. Now think about whether that seems reasonable given the graph. Does it look like we have 2 and approximately 5/6 of a unit? Because if you took obviously the 2 whole squares make sense, and if you took the half triangle and sort of a almost half triangle here together, that seems reasonable that would be the correct answer. So we'll leave it here. We don't need to put any units. On the AP exam, you could leave it in the improper fraction form. You don't even have to simplify if you don't want to. In fact, as we've discussed earlier, if you don't trust your mental math skills, you can leave it just like this, or even just like this. And don't worry about doing the computations on the AP exam. If your arithmetic or the thing that you've written on your paper can be typed into a calculator by somebody reading your exam and you'll arrive at the correct answer, then that is sufficient. A lot of people, unfortunately, will struggle getting a common denominator in a timed exam, and Just don't worry about that. Just try to set it up correctly and then leave the arithmetic to the person grading your paper. All right, second example. Find the area of the region bounded by the graphs of f of x equals 2 minus x squared and the graph g of x equals x. Sketch and shade the region. Now notice in this example, we don't have any vertical lines, so we're going to go to the intersection. And so when you don't have vertical lines, you need to find the intersection of the two graphs, and that will be the bounding of the region. Let's graph. Again, I'm just going to use red and blue to stay consistent. I'm going to do the top one, 2 minus x squared. We have a y-intercept of 2. And in this case, if I want to sketch this parabola using my table method, so I have x squared, and then my a value is -1 times x squared. I have -2, -1, 0, 1, and 2. I square those numbers, 4, 1, 0, 1, 4. Then multiply them by the leading coefficient, -1. And so I get -4, -1, 0, -1, -4. I graph that from my vertex, which of course is going to be at 0, 2. And I just go left 2, down 4. So we're at -2 here. Left 1, down 1. 0, 0, 1, -1. 1, 2, down 4. And then just kind of sketch the graph. All right, there you go. There's the parabola. Let's do the line y equals x. So then we just go at the origin, go 1 over, 1 up, like this, and then connect all those dots. And you can see clearly they intersect at lattice points, or the nice graph grid line points, which is great. And we see the intersection in the first place is -2, -2. That's the first intersection. And the other one's at 1, +2. Now when we're looking to find the region, we're going to be caring about those x values, because when I set up my integral, that's the bounds of the definite integral. And so I'm going to go from -2 to +1. And the region I'm looking for, again I'll enclose in orange, is going to be right between the parabola and that blue line. So this is the region I want, and of course my highlighter is not going to be inside the lines. That's an elementary school thing that I struggled with. Can't color in the lines apparently. So there you go. That's the region I'm trying to find. And of course, which function is greater than the other function, the parabola or the line? Well, again, when I ask that question, think about which graph is vertically higher in this case. Since they're functions of x, we're looking up and down, and the y-axis, or I'm sorry, the y values that are higher are greater. So in this case, the red parabola is above the blue line. And so when I set up my integral, it's going to be the function 2 minus x squared minus the lower function, -x. I'm sorry, that's +x. My mistake. -x was the last example. So let me fix that. There we go. dx. Now before I integrate this, you can sort of simplify the integrand and combine what we have going on here. We would have 2 minus x squared minus x dx. And if you'd like, you can just rearrange that. And so -2 to 1, and let's put it in standard form so that -x squared comes first, minus x plus 2 dx. And then just use the fundamental theorem of calculus and the anti-differentiation rules that you know. And so I get -x to the third over 3 minus x squared over 2 plus 2x evaluated from -2 to +1. So start with the upper bound 1, get -1/3 minus 1/2, plus 2, excuse me, and that's the upper value. Subtract the lower value, and so it's going to be -2 to the third. It'll be -8 over 3, and then minus 4 over 2. And again, I'm squaring that -2 to get a +2, and there's a negative in front, so it stays negative. And then minus 4. And if I were you, I would leave it just like this. It's not very usable, but that would get you full credit on the AP exam, especially if you're worried about your mental math skills. Now, in a multiple choice question, this isn't going to help you. So just for the sake of that argument that if this is perhaps a multiple choice question, I'm going to get a common denominator of 6 and then just try to go through and make this all work. So that's +8, so times 2 is 16 over 6. And then we have minus a 12 over 6. And then, oh boy, 24 over 6. Distribute that negative sign, we get negative, and let's combine some of these. Negative 2 minus 3 is negative 5 plus 12, and so that's going to be 7 over 6. And then minus, distribute that negative sign, and I get negative 16 over 6, plus 12 over 6, and then plus 24 over 6. And let's get the adding done. 12 plus 7, I'll just go left to right this time. 7 minus 16, that's going to be negative 9 plus 12. And that is going to be 3 plus 24, 27 over 6, or 3, and looks like half. Nope, 4.5, 4.5. Because that's going to be 4 3/6, 4.5, or 4.5. Now again, just to see the suitability of our answer here, does that seem reasonable that you might have 4.5 squares included in that orange region? I know I have one there. Maybe, these two can make one here on the outside. Yeah, I think that seems reasonable. Hopefully I did my mental math right. But if I made a mistake, that's just further driving home the point that you can just leave it here on the AP exam if it's a free response question. I just know that sometimes it'll be multiple choice. I want to make sure that you get that correct if you have to choose. This is example 3. I must have forgotten to number it here, so my mistake. Find the area the regions bounded by the graphs of f of x equals sine of x, f of x is sine of x, and g of x is cosine of x. Sketch the graph and shade the region. All right, sine of x, initial value of 0. At pi over 4, that's 45 degrees. Sine would be 1. Pi over 2 would be 0. Down at 3 pi over 4, negative 1. Oh, I'm sorry. I'm totally botching that up. My mistake. So I'm sorry. At pi over 2, we'd have 1. And at pi over 4, it's going to be square root of 2 over 2. So it's going to look something like this. My mistake. Sorry, everybody. All you trig people are yelling at your computer screens or iPad screens right now. So there's the first function in red. And so the same thing's going to be on the other side, just negative. So there's sine of x. I was not paying close enough attention to my x-axis labels. Cosine of x is going to start at 1. At pi over 2 is going to be 0. And then at pi is going to be negative 1. And same thing mirrored on the other side. So in that case, it's going to look like this. And so we did not have a domain restriction, but we would have to. Otherwise, we're going to have an infinite number of regions. You can imagine if these graphs continued onward periodically, there would be so many regions enclosed. And so we're just going to pick the intersection that's on this graph. And typically, they'll tell you on the closed interval, let's say from negative pi to positive pi. And I must have forgotten to type that in here. But of course, you should always have a domain restriction with these trig functions. Otherwise, since they're periodic in nature, they'd go on forever, and you'd have tons of regions to find the areas for. So in this case, we're going to find the area of this region right here. And if you went from negative pi to pi, I should state here too that I would also include these regions on the outside, like this, and this region here too. Now this is a good example because at this point you can see that when we have to decide which one is greater than the other one, there are times where they switch places. Okay, so if I look, again I'm just going to color in because I'm too OCD here. The first intersection point technically is the vertical line x equals negative pi. That's the first integral here. So the first one I'm going to set up would be from negative pi to the intersection point right here, which looks like it happens at negative 3 pi over 4. And in that case, in that small interval from this vertical line to that point here, the red function is on top. So it would be the sine of x minus cosine of x on that interval dx. Then, they switch places. So now from this intersection point to the upper intersection point here at pi over 4, we know that from negative 3 pi over 4 to positive pi over 4, now cosine is on top. So that's going to be here, cosine of x minus sine of x. And when I say on top, that's kind of being loose in my mathematical discussions here, vocabulary. It actually means that the function cosine of x is greater than sine of x on that interval from negative 3 pi over 4 to pi over 4. And then, of course, the last integral we're going to set up is going to be from positive pi over 4 to, it looks like the vertical line over here, x equals pi. And in that case, they switch places again, and sine of x is again the greater function minus cosine of x, which is the lesser function. Now, for the sake of time, this video is already getting a little bit longer than I wanted it to. You could do this on your own, either using a calculator or using your anti-differentiation rules and what you know about trig functions. Make sure that you use your unit circle here. But you could eventually get the area of the region enclosed by these graphs on that closed interval from negative pi to pi. All right, thanks for watching. Hopefully that made sense. Remember to respond to my email about when we can meet on Wednesday, March 18th. Your options are 8:30, 9:30, or 4 p.m. 8:30 a.m., 9:30 a.m., and 4 p.m. Please respond to that email as soon as possible, and hopefully I will see you via Skype or Zoom soon. Have a great day.